my name is Jake Bernstein, and today I'll be walking you through my Physics 2212 Lab 1, which is concerned with charged tape. So a brief overview before we dive in. I've sliced the project up into 4 different segments. One is the introduction, in which we'll cover purpose, concepts, formula, setup. Then we have our experiment, then computational model, and finally, discussion and conclusion. So to kick it off, here's the purpose. We aim to empirically corroborate key physics principles relating to the interaction of 2 charged objects by observing the interaction of 2 pieces of charged tape when brought close together. The overarching question that we hope to answer is how many atoms in the charged tape lose an electron in the exchange. And to back up our experimental process, we'll model the motion of these 2 objects using VPython and compare these 2 results. And just a brief preview of our results is that both models produce pretty much the exact same data set, and this corroborates the key physics principles of the lab. So some key concepts we have here are that one is Coulomb's law. Coulomb's law states that objects with the same electrical charge will repel each other and objects with the opposite electrical charge will attract. Since Coulomb's law only applies to point charges, we were required to make the drastic assumption that the charged tapes act as point charges. We will go more into detail about this later on. Finally, any system on Earth is susceptible to the effects of gravity. As such, the force of gravity was accounted for in our calculations. And here we have on the left Coulomb's law. Another adaptation of it is that F is equal to QE, which is not included but inferred. And then we also have the force of gravity, which we all know from Physics 1 is just F equals mg. Here's our experimental setup with a shoddy little drawing on the bottom. Our system is the 2 charged pieces of tape, and the surroundings is the earth, blocks, and the table supporting it. So first we prepared 2 pieces of tape, then we charged the tape, then we mounted them one on top of the other and recorded the data of the interaction. Here's the experimental work behind it. So I'll refrain from walking you through it, but some key figures we see are the force of gravity, 1.47 times 10 to the negative 3 newtons, which is equal to the force of the electric force. And then we have our charge as detailed, number of deficient electrons, number of atoms, and then the percentage yield. And I'll walk you through the same process in the coding aspect, which is right here. So we have the code, we've defined our constants on top. Then we calculate the gravitational force, just F equals mg, and that is in the negative y direction. Then we have the electric force, which is equal to the gravitational force since the object is suspended at rest. And then we calculate the charge by rearranging Coulomb's equation to get Q. The number of deficient electrons is just Q divided by, the charge of 1 electron. Calculate then the number of atoms, and then the ratio of the electrons to the atoms, all displayed over here. And here's a little diagram for you. Now we have a comparison. So some key assumptions across the experimental and computational experiments are that we treated the long tape as though they were point charges, which is obviously not real life, but for simplicity's sake we did so. And we assumed that there was an even charge distribution on each tape, which we all know is also not true, but it's a simplifying assumption. As you can see on the right, all of our figures were concurrent across the experimental and computational model. So the bigger picture is simply that Coulomb's law was verified through these results and the unilateral nature of it. And we're able to model the interactions of the charged particles using the point particle model because the charged tape reacts very similar to point particle. Now, some possible errors in this lab are that we could have accidentally touched a piece of tape, and we'll talk about the adverse effects of this on the next slide. Some imprecise measurements, which are always a factor, human error, and then an uneven charge distribution, which is one of our assumptions. Now, conclusively, we have these 2 guiding questions, and the answer to the first one is if hypothetically electrons had positive charge and protons had negative, there'd be no change to the results since it'd just be flip-flopped. They would still have like charges and they would still repel the 2 pieces of tape. And then secondly, it is extremely important to handle the charged tapes as little as possible because our skin is conducive. And this means that if the tape comes into contact with our hands, there will be a transfer of electrons, and our results would be significantly skewed. That's the end of our lab. I hope you enjoyed and have a good rest of your day.